Hello, welcome back. I'm Ralph, EI2KU, and today we're going to have just a very quick look at decibels, dB's, dBm's, what they are and why we use them all the time, I guess. So we're going to start with something we all know, or not familiar with, I hope, and that's Ohm's law, V equals IR. There's a nice simple test for you. A circuit with a 100 ohm resistor, it says it's 2 amps, so how many volts? How many volts is it? Okay, V equals IR, 2 times 100, 200 volts. A bit of an odd example, but never mind. So Ohm's law, basis of a lot of calculations we do. But when it's dB's, dBm's, we're talking about power. And the definition of power in a DC circuit, at least, is VI. Now, I hope you're also familiar with the Ohm's law triangle, which makes it easy to juggle around the parameters in the equation. So V equals IR, or I equals V over R, or R equals V over I. And we could use that to make some substitutions in the power equation. We can replace V with IR, or we could replace I with V over R. And when you do that, you get this. Now, obviously it's I times R, so it's I squared R. And the same thing happens with V, you get V squared over R. And the reason I'm showing you this is these two squared terms are important because power is really follows a square law. And what that means is if you plot it on a graph, it looks, here's an example, something like this. So the bottom end is compressed down near the origin. The top end scoots off to really big numbers up off the top of the screen. And that makes it difficult to make measurements, draw conclusions from the graph, or even to display it on a monitor or something. You know, the numbers can be very small and they can be very big, difficult to handle. And that is at least one reason why we use logarithms. We convert it to a log scale. Now, log scale is really a ratio. You can see how it says P1 over P2. But I'm not going to dwell on that equation too much. The important thing, though, is that when you do that, we change it to logs. Oof, you come back to a nice linear straight line. So you can now represent the figures on a graph, on a screen, or whatever, in a much more controlled way, a much easier way to understand. And you can go from the very small to very big numbers without any problems. So that's really why we use logs for that. Two ratios worth keeping in your head. A 2-to-1 ratio in dB's is 3 dB's. So if you double the power or halve it, then you're changing by 3 dB's. 10 times is 10 dB's. So going from 1 watt to 100 watts, for instance, is a 10 dB change. Those two ratios are worth keeping in your head because you can usually work it out. You know, if you say a 12 dB change, you can get there by saying, well, it's a 10 plus nearly a 2 ratio change. We're supposed to, most of the time we work in dBm's, and there are some m's missing from this slide, apologies. So 1 milliwatt is 0 dBm, should say dBm, because it's a reference we've chosen to use. It's an industry standard, and that's what it means, a dBm, 1 milliwatt. And a couple of examples: if you go up to 1 watt, that's a 30 dB change, takes you to 30 dBm. 100 watts is 50 dBm, and that's 100,000 milliwatts. So you can see why, in many ways, it's easier to handle with 50 dBs and work out it's 110,000 milliwatts or something. So that's dBm's. You sometimes see dBw's, which are referenced to 1 watt instead of a milliwatt. But dBm's is what we nearly always use. Now, the other thing that dB's is very helpful for, very handy for, is you can do the sums very simply. I mean, here's a simple example: a transmitter, an amplifier, some cables, and an antenna. So, how much power is going to the antenna? I've chosen 42 dBm, which happens to be is roughly 15 watts. You got a 12 dB amplifier, that's not uncommon, 10 maybe, and then some losses in the cables. And if you want to know how much power is going out to the antenna, you just add them up: 42 plus 12 minus 2. Whereas if you're working with 15 watts plus multiplication of something or other and some resistive losses in the cables, it's a complicated sum. Whereas in dB's, it's very easy. So that's another reason why we like them. And then just lastly, a quick look at something sort of relevant to our normal radio stuff is the SWR meter, which we all tend to fixate on. Maybe a topic for another day, but I think most of the time you should just ignore an S meter. The convention is that the difference between an S point is 6 dB's. And if you remember, 3 dB's was doubling the power. So between S points, you're doubling it twice. And to give that some perspective, if you were to go from an S7 to an S9, then obviously that's 6 dB's twice, S7 to 8, 8 to 9. So that's a 12 dB change. And if you were on the air and you're talking to somebody and you said, "Oh, you're a 5 and 7," and you're like, "I'd rather be 5 and 9," and you're running a 100 watt, fairly standard 100 watt transmitter, then how big an amplifier would you need to make your signal S9 in that situation? Any guesses? Well, I can tell you, you'd have to go up to 1.6 kilowatts. And I think we all know that there's not a huge difference between an S7 and an S9 when you're listening to somebody. So don't worry about it. So the two things to take away is really, we use dB's in order to handle a big range in numbers. So you can go from really small to really big easily. The 2-to-1 ratio is 3 dB's, 10-to-1 ratio is 10 dB's, and ignore your S meter. If you can hear the guy, that's fine. Lots of power causes lots of problems. Okay, so that was just a quick look at dB's. I hope it helped. And once again, if you've got any questions, let me know. 7 3s.